Hello students, my name is Shayan Mitra, faculty member of Department of Electronics and Communication Engineering, Greater Kolkata College of Engineering and Management. Hello students, my name is Shayan Mitra. I am the faculty member of Department of Electronics and Communication Engineering, Greater Kolkata College of Engineering and Management. Today I am going to taking the class of electromagnetic wave. Subject code is EC501. And so let's start with the class. Today's topic is about the different kind of coordinate system and its transformation between three of them. There are three different kind of coordinate system we have. One is Cartesian coordinate system, another one is spherical coordinate system, and another one is cylindrical coordinate system. So first we will be talking about Cartesian coordinate system, then we will be talking about cylindrical coordinate system, and after that the third and the last one will be spherical coordinate system. So we will begin our explanation about the Cartesian coordinate system. These are the three choices we have already said about it. Okay, let's go to the next slide. And this is the Cartesian or rectangular coordinate system. As we can see from the XYZ coordinate, that if we draw a parallel line if we draw a parallel line with Y and parallel line with Z and a parallel line with X, we will get a rectangular shape 3D area. Rectangular shape 3D area. And here it is. This is the x-axis, this is the y-axis, and this is the z-axis. We can see that if we take the proper space of x, y, and z-axis, that if we take the universe as a Cartesian or rectangular coordinate system, it will be started at minus infinity and it will end at plus infinity, and it will be similar or same for y and z, all three of them. Three different axes through which we will define our different kind of physical quantities, different kind of space variables will be defined on the Cartesian coordinate system, and the three different variables or three different parameters through which we describe Cartesian or rectangular coordinate system are x, y, z, and their upper limit and lower limit is plus infinity to minus infinity. Now we have already discussed the vector algebra. Now we know that if we have a vector A in Cartesian coordinate, that can be written as A suffix capital A suffix x into small a suffix x plus capital A suffix y into small a suffix y plus capital A suffix z and small a suffix z. What it really means is, if there is a vector, now we have that vector defined by suppose we have to explain or describe the vector in Cartesian coordinate system, we will use what we will do, we will divide the three components of A, one along the x-axis, one along the y-axis, and another one along the z-axis, and a suffix, the small a is defined the unit vector. So one vector A can be defined using these three different vector components, and this denotes that this vector is along the x-axis, this vector is along the y-axis, and this vector is along the z-axis. These are the unit vectors along the x, y, z direction. We will get the total value of, now if we take the summation of these three vectors, we will get the vector A which reside in the Cartesian or rectangular coordinate system. So let's go to the next slide. Now this is the rectangular coordinate system where the origin, and in origin the y, x, y, and z is equal to 0, and these are the coordinate system, coordinate system, and this is the pictorial depiction. Now let's go to the next slide. Now this is an important factor that we need to understand, that what is differential volume element. Now suppose in Cartesian coordinate system we have a cube. This is a pictorial depiction of a cube. Now if we have to uh, extract the volume of this cube, now what this cube really defines, this if suppose this cube is very element, it's a very elemental cube which has a very small length, in length, width and height. The length, width and height in three direction we will get x y z axis. In x y z axis we have different values. Length is according to the x axis, height is according to the z axis, and width is according to the y axis. Now if we multiply three of the variables or three of the quantities, what we will get the volume of this very small cube. Now this is the volume, dx dy dz. D here, d basically define the differentiation or the differentiation value of length x. It means it's a very infinitesimal small length. This is infinitesimal length, width of y, and this is the height which is very small. This each dx dy dz represent a very small value of length, width and height. Now if we take a volume, if we multiply these three, what we will get? We will get dv, that is the very infinitesimal small volume of this cube. Now this, if we take this is the surface area. Now this is here, this is the surface area. Now if we have to find the surface of this infinitesimal small area, what we will do? We will, if we have to find the surface, what we will do? We multiply the length and the width. Now if we take this surface, what we will have? We have dx dy. This is the length and this is the width. Now if we multiply both of them, we will get the surface area. Now according in this surface area, the z vector of the value of dz is not considered. Now this surface area has a direction. The direction, if a vector has been represent, if we represent a vector using this surface area, the direction of that surface area is along the z axis. That's why this z has been written. Now this z is basically nothing but a suffix z, which is a unit vector, and it's also indicating the direction of this surface area, and it will be similar for each and every surface. Now if we take this surface, here we have considered dz and we have considered dx. Now if we multiply dx and dz, we will get the surface area ds, and this is along the y axis. Now this has been, now this is represent as ds suffix y, and this, the whole vector has been represent, and the direction will be in accordance with the y axis. And this is also similar to the same. We can use the same process to find the value of this surface. This is the surface area of the cube. The value will be dy and dz. Here is the dz and here is the dy, because z axis according to the y axis we will get the surface area. Now if one vector has been represented, if suppose the surface area is representing a vector, now then that vector will have a direction, and the direction of that vector will be towards the x axis. That's why this s suffix x has been mentioned, and this x, this is basically unit vector a suffix x. It has been written in this way, and this is the total volume of the cube, and the volume of the cube it will be a scalar product. It's a scalar quantity, but surface area is a vector quantity. Why? Because this surface area is representing a vector which is in the direction of the another axis. Now we have already know how the cross product and dot product has been working on. Now suppose if you have a cross product of x and y, the resultant vector will be in the direction of z axis. The same similar feature has been introduced in surface area, in case of surface area, in case of any kind of surface area which has been uh, represent or yes, represent using dx and dy. Now if we multiply dx and dy, we will get ds. Now this ds will be in the direction of, now this yes. Now the ds and dx and dy, if you multiply them, we will get the magnitude of this surface area, and the this surface area will represent the product, the magnitude of the vector ds suffix z, and the direction will be in the along the z axis, and that is the direction of this specific vector, and the volume will be a scalar quantity. Okay. So we have ended this. I will go to the next slide. Okay. Now the vector expression in rectangular coordinates are general vector, which will be described in this way: b suffix x, a suffix x, b suffix y, a suffix x plus b suffix z and a suffix z. This is the magnitude of b. This will be represented in this way. Now if you have to find the unit vector in the direction of b, we will do this. This is the magnitude, and we will divide the whole vector using the magnitude, and only the direction will be left out. So this is the formula, or the this is the way of finding the value of the direction of the unit vector. We will find the unit vector this way. So let's go to the next slide. Example. Okay, so this one. The specified unit vector extending from the region toward the point g 2 minus 2 minus 1. This is the problem. Now this is the expression of that vector. Okay, so using that we will find the magnitude of vector g, and that will be 2 square minus 2 minus 1 whole square. We will just, this is along the x axis, y axis and z axis, so that each value will be taken. We will get the summation of the squares of the individual vectors, and then we'll take a wholesome root. Then we'll get the magnitude of that vector. This is the magnitude of the vector, and the value will be, now if we just divide them, we will get this. This is the value of the unit vector. We just divide the whole vector. This is the vector, and we will divide the vector with the magnitude, and we will get this value, and this is the value of the unit vector. Okay. So let's go to the next slide. Okay, and now this is we will describe the differential length, the area and the volume in Cartesian coordinate system. Now how it will work? Now as we have already described how the differential area has been, we used to extract the value of differential area. We have already described all these things. If you have to find the value, the surface area along the x-axis, the product of dy and dz, and this is the unit vector which describes the direction of that specific vector. But in this ds can be described using each three of them. Okay, and this is the differential volume, which is a scalar product or scalar quantity, as you can see. And this is the differential displacement. How this works? This is the displacement value. This is the similar displacement value. It will be infinitesimal small value of dx, which is multiplied with a suffix x, and this is the y suffix x, and this is the z suffix x. It means that any value of x, if we take a differential value of dx, we will add the value of x, the y and the z, and we will get the differential displacement value. Okay, yes, in this way, this is the differential displacement value. Now if we take a summation of dx, dy and dz, we will get the value of dx. This is the whole differential displacement value. Let's go to the next slide. It means basically it basically refers that the displacement of a specific vector can be described by the differential value of along the x-axis, differential value of the y-axis, and differential value of along the z axis. Now if we take the summation of all these three elements, we will get the total differential displacement value of the specific physical quantity, which is a vector also. Now we will start to understand the that is the end of the Cartesian coordinate system. Now we will describe the cylindrical coordinate system, how it works. Cylindrical coordinate systems. Any point in space is considered to be at the any point in space is considered to be at the intersection of three mutually perpendicular surfaces. One, a circular cylinder, rho, which is constant. Rho will define the radius or the distance of the specific point from the center point or center line of the cylinder. That is the vertical plane, that is also which is phi is equal to constant, and this is the horizontal plane, that is z constant. In case of z is equal to constant. Now if the value of z will be constant, we will have a horizontal plane. If we have phi constant, we will have a vertical plane. If the rho is constant, we will have a circular cylinder. It means the rho is the value along the center line of a cylinder. Now if that rho is constant, what will we get? We will get a constant circular cylinder. Now it is self-explanatory always, and this is the vertical plane. In case of phi is constant, we will get a vertical plane. Any point in space is represented by three coordinates: rho, phi, and z. Rho denotes the radius of an imaginary cylinder passing through P, or the radial distance from z axis to the point P. We can remember it using any of these two. That one is rho denotes the radius of an imaginary cylinder passing through P, or the radial distance from z axis to the point P. Now that rho will only define the distance of the specific point P from the z axis, and it means the all along the z axis we can take any point, and we will only the radial distance will be measured. The radial distance will be constant all along the z axis of a specific point P. Phi denotes azimuthal angle measured from x axis to a vertical intersecting plane passing through P. Now it's an important point. Phi has been named as azimuthal angle. Now measured from x axis to a vertical intersecting plane passing through P. Now if suppose there is a vertical plane passing through P, if there is a point P, there will be a vertical plane which along it will be passing through P. Now the distance of that specific vertical plane from the x-axis will be denoted as phi. Now phi is practically a constant. It will be defined as, it is a value will be between 0 to 2 pi, but this is a measured angle, and it will be measured from x-axis to a vertical intersecting plane which is passing through P, and z denotes the distance from xy plane to a horizontal intersecting plane passing through P. It is the same as in case of rectangular coordinate system. In case of rectangular coordinate system and in case of cylindrical coordinate system, the value of z is same. Let's go to the next slide. Cylindrical coordinate system. Now this is the pictorial depiction of a cylindrical coordinate system. Now this is the z axis, this is the x axis, and this is the y axis. Now the value of rho will be in between 0 to infinity, because as you can see, the value of rho can't be minus phi, because if we taking the whole universe as a cylindrical space, then there will be in the very middle of the cylindrical space there will be a z axis which will be along to which will be in the line of the center of the cylinder. Now suppose that how we will manage to get a cylinder. We will take a circle, we will take a two similar circle and we will join them with their constant radial distance. So this is the circle. Now there is a center of that. Through that center line up to the another center line there will be a straight line, that is the z-axis, which we have already described. Now if we take the whole universe as a cylinder, the value of rho will be from 0 to infinity. That's why it will be between 0 to infinity. Now the phi, which is the azimuthal angle, will be, because it is an angle, it will be, the range of phi will be in between 0 to 2 pi. As simple as that. Now the value of z will be in between minus infinity to plus infinity, because it's a continuous space, because there is no specific limit of z-axis, because we can stretch it to an infinite limit. That's why the value of z will be in between minus phi to plus phi. So let's go to the next slide. Now okay, one thing that yes, there's another thing this picture is explaining, that suppose the value of phi is constant. Now what we will get, if the value of phi is constant, we will get a vertical plane, which is, this is the vertical. Suppose the p is in there. Now the value of, if suppose we have a constant value of phi, then this vertical plane will be created. Just like in case of x, y, z. Suppose we have a Cartesian coordinate system x, y and z. Now suppose y is equal to some value is equal to 5. Now at the p, the value of y is equal to 5, there will be a vertical plane which is parallel to the z-axis and vertical to the y-axis. The same thing is considered here, that if the value of phi is constant, there will be a vertical plane. Now the same thing will happen. Now if z is equals to constant, we will get a circular plane. Now if rho is constant, we will get a same circular, if rho is equal to constant, we will get a circular cylinder. Now if z is constant, we will get a horizontal plane. That we have described earlier here. Now in case of z is constant, we have a horizontal plane. In case of phi is equal to constant, we have a vertical plane. So yes, this is the pictorial. Now if we put rho is equal to 3 or any kind of value, now for phi is equal to 45 and z is equal to 8, we will get this kind of a picture. In case of rho is equal to 3, horizontal A. In case of rho is equal to 3, then we get a same circular cylinder of radius 3. If z is constant, where the value is 8, we will get a horizontal plane, and in case of phi is equal to 45, here we get a vertical plane which touch the point P here, and this is the magnitude of the vector is given. Okay, so this is the transformation of x is equal to rho cos phi, y is equal to rho sin phi, is equal to z is equal to z, and we will going to describe how this equation and the different kind of equation of cylindrical coordinate system in the next lecture. Thank you.